type of my space.
Looking at
That's my script. The A, B, C, D, and E, F concurrent, right? The concurrent lines no, I talked about A, B being in line. What do I mean there? I mean the exterior product of A and B is points, right? In the algebraic formulation. This is a piece of line along a specific the specific projective line containing the points A and B. The size of this has to do with the length between A and B in your picture, but also the size of A and the size of B. So there's a question of size. So pieces of space of determinate volume in their own space. And you can write this in the Cayley or piano space or Cayley algebra as in AB, we want to take a meet with CD, and then that should give us something like a point, and then we can this point will be on EF if the join of that point with E and F, that point together with E and F would be a dependent set, so the exterior product would be 0. So join EF, so 0 equals. But this in this Cayley algebra you can expand as let's see, which one did I do it? There are two ways to do it. You can take the A with CD. You split this into two pieces here. Fill a bracket here, A, C, D, but not inside a bracket, but you make a piece of plane with A and CD, tensor B, but then you have to split the other way, and then B, C, D, tensor A. So this splitting operation occurs here. If that is 0, if and only if the lines are concurrent. But this means that these two monomials have to be equal. And that, as I say, is a property of a larger matroid than just A, B, C, D, and the F.
Hold on, man. Where did EF go in this expression? So you just rewrote the expression A, B, V, C,
C, D.
Oh,
it's sorry, it's here, EF. Thank you. Sharp this morning. Yeah. This is a piece of the plane of A, B, C, D, E, F, right? This is also a piece of the same plane, right? So we have the tensor product of two pieces of the same plane, and that should be, for this to be 0, that should be equal to this. So it's a question of sizes of triangles and weighted points in a single plane.
But now you have this cross product. You have a V and you have a V. So is this multiplication, is it equal to one of these other symbols, or?
Oh, which
tensor product
yes.
on the right.
Yes, on the right there's tensor product.
Yeah.
But this tensor product is not the same as...
Absolutely, you're right. It has to be, it is a little bit more, one has to go deeper a little bit in that fact. Yeah.
Mm-hmm. Okay.
We could go deeper in another moment.
Okay.
In order not to stop and read.
Okay. Okay. So you recall the P relations from Hodge and Padova, I expect, when you have a dependent set of A, B, say ABCD equals 0. The relation between A, B, C, and D is the point A multiplied by the bracket BCD minus the point B, the bracket of ACD, etc. So you get an expression like, which way did I write here? ABC D minus ACD B plus the 4 terms, right? So these are whenever you have 4 points in the plane, you will have this. But the way we finally realized we could do would be to eliminate the bracket and just write this, but tensor. Sort of back to Grassmann. And this is 0 as the standard linear combination. It's a unique linear combination of the 4 points in the plane up to an overall scalar multiple. So what's that? Now. This in fact was the beginning of the idea with the algebra was to deal with expressions like this and drop down and deal with an algebra of pieces of space rather than pseudoscalars and vectors. And let me see, I'm a little lost here. But in fact, not only do if A, B, C, D are coplanar, A, B, C, D dependent set in Matroid, not only is this expression 0, but any other expression of any of these 5 forms is equal to 0. Namely, you can take 1, which is basically 1 times the empty set of points. 1 tensor ABCD. ABCD is itself 0, so its tensor with anything is 0. We can split as I did here, but we can also split 2, 2, or no, the shape 1, 3, 2, 2, 3, 1, 4, 0. All of these are equal to 0. If you add them all up, that is what algebraists call a coproduct, and it sends the delta or some sort of operation. It's a coproduct of A, B, C, D equals, and it's the sum of all these things here. These 5 individual pieces of that expression of the different shapes we call the homogeneous slices of that.
Henry, can you just say that again? I didn't quite. If you add them all up, that forms the co-product. So what do you mean by? You take all of those relations.
Yeah, not all the relations, but all the expressions.
All the expressions.
Yeah, the sum. This sum is without the equal signs. is the co-product
of those things. Oh, I see.
Then we write, for instance, this one we would write as co-product slice 2, 2 of ABCD. That's what we really deal with. In almost everything you do in Matroid theory, you're dealing basically with one homogeneous slice of this algebra.
So that
go ahead.
No.
So it's sort of like a graded algebra, something like. You tell me, I'm just.
Is that?
It's a graded algebra. Like
Yes, it is. It's graded by shape and content. And the reason being that we're dividing up a homogeneous ideal, and we'll say why.
Yeah, thanks.
Yeah, in fact. So this was the birthplace of the Whitney algebra of Matroid. You start with letters for the points of the Matroid form words from independent sets of points, which represent pieces of flats, right? Portions of flats in the Matroid, so that we and then think of it as an exterior algebra of n, and consider consider tensor products of these words. So we arrive at a stage where we can say that that these well, yes, we can arrive at a stage where in this, here it is here. Here I want to be able to say that AB tensor CDE equals AC tensor BDE. Oh, I wrote them down there. Okay, that's all written out. Okay, so here we go. So in this Matroid, we have a piece of this line tensored with a piece of the plane, CDE, is equal to a longer piece of line tensored with a smaller triangle, or either triangle area like here. Right? The other one was like this. So the proportion of this big triangle to this little one is the same as the proportion of this big line to this sort of the AB and AC. AB and AC, and they're inversely proportional to their paired triangular areas. I would dearly love to understand much more of what the algebra doing geometrical thinking at that level. But this in fact, this idea of algebra of pieces of space, this is very much at the level of what Grassmann was doing in 1844. He unfortunately found he could not stick with that. He had a very nice geometric product, which he called what is it called?
Regressive.
Regressive. There's nothing regressive about it. The Vacquerie school almost explains that the regressive product is just the dual of the exterior product, which is false. In fact, Grassmann's product is a product which gives the joint and the mean, the joint tensor mean, and the fact that the scalar sizes can split from one piece to another, as they do here, and have equality here, is the origin of the idea of tensor product. And if you happen to grow up like me as a physics student, you actually learn how to write tensors and compute with them. I don't think anybody does it anymore. They just say it's a tensor. No. Well, here are four coplanar points in 3 space. Here's the exterior product of AB. Here, so this minor of size 1. Sorry for using the word minor today. Minor of size 1 here. The determinant is here. This here is this one, etc. So the 2 by 2 determinants here are listed here for AB and for CD. Now AB tensor CD is this matrix. You put AB here and CD here and you multiply. Now how many of you know that? Perhaps because I felt so happy to have listened to all these terrible engineering professors at the University of Michigan talking about mathematics. They had a great mathematics department in another building, but this is what they taught. I find it very useful now. And this is a matrix of rank 1.
So I don't understand exactly that matrix. I understand that the row and the columns are the blue coordinates of the subspace.
This is a multiplication table for them.
And what is the meaning of that multiplication?
This is equal, this tensor can be represented and added to other tensors, etc. if you recognize that it's a 6x6 matrix and you add them component-wise.
Oh, so you mean that the entries of the matrix are the components of that tensor in a suitable basis of the tensor?
Yes, yes,
oh,
yes,
I understand.
Good
So
point.
when you have a sequence of elements like AB or ACE, these are always Grassmannian coordinates?
Oh, I'm mixing two things because I'm dealing with real exterior algebra at some point in my talk, but I'm also dealing with construction of the Whitney algebra, which is not numerical like that. It's figurative with names of points.
Yes, in a sense, if you have an abstract Matroid and you have a representation of the Matroid, then you will have the Whitney algebra of the Matroid and something on the vector space that is essentially the tensor powers of the exterior algebra of the vector space, where all these Grassmann things live.
So am I safe in thinking of these things as Grassmannian coordinates?
When they are realized, when
When
Matroid
they're
is
realized, yeah. So in my head, I will always have a realization,
Okay.
and then I think of these things as Grassmannians. Okay, that's good. Thank you.
Yeah. So the definition of the Whitney algebra is then the tensor power of the free exterior algebra on the set points modulo the ideal, it's a homogeneous ideal, modulo the ideal spanned by co-products of dependent sets.
But I guess circuits are enough.
Circuits are enough.
Yes.
Absolutely. So I wrote a Python program to carry out these operations to straighten the monomials in any given shape content slice. Oh, I should mention again at that point that because this ideal is homogeneous, then this is graded by the Whitney algebra is also graded by shape and by content, so you can compute internally to a shape content slice and do everything there. And so the straightening is to express some positive integer multiple of each monomial. I didn't say just express the monomial, but express some positive integer multiple of the monomial. And so you're going to need two if you're going to do Fano. As an integer linear combination of standard monomials, which are all earlier than that one, earlier than the one you're trying to straighten in lexicographic order. So we generate all the elementary syzygies, elementary relations from, we form the matrix of the integer coefficients and reduce it to a Hermite canonical form. In the paper, there's a picture of the Hermite canonical form. You have a matrix with certain pivot elements here. The pivot elements have to be positive integers, and then to the right and up here, you have zeros, but beneath here you have positive positive integer entries which are less than the pivot value, and then to the left you have our arbitrary entries. The pivot columns here are labeled by monomials which are non-standard, and the non-pivot are labeled by the standards. If you do the Fano, you will find that you have a pivot element sitting way over here in the last column, so that twice it is 0. So you're going to have, well, 2 is 0 anyway, if you're in the right field. So the Whitney algebra is itself a bi-algebra with a coproduct and product. The coproduct being multiplicative, and the product having this property. This is a product of two monomials. Each thing in the first place here has to go over in the first place here in its right position. If you put, well, of course, if you change two things here, it's still a monomial, but you get a negative sign out front. If you change anything, change the order of any pair. But you notice that D here, to get home over here, it has to pass G, E, D, B, and E an odd number of points. So this will generate a negative sign here. All the other guys here, F has to get here. It has to cross D and G to get there, so that's even. All the other crossings are even. I did that on purpose. So, just one minus sign there. So that's called a twist in the product operator in the Whitney algebra. For representable matroids, there is a classical method for straightening due to Rutherford by interpolation. And in the paper that I give you, I won't try to just describe that, but in this paper we have on this page, it's almost at the end here. There's a heavy form which is shown there, and opposite it is a big picture of the interpolation method. The idea is we have the standard monomials at the top listed in such a way that in columns going down there, they're strictly increasing in the vivid order, and sometimes there are places that have to be left empty called holes. And so at the top left here, vertical, we have the same standard monomials, and then we try to interpolate those into themselves, and then below we try to interpolate the non-standards into the standards, and we will get a certain numerical matrix. The idea is that you are allowed to, in moving from the left border here into a symbol in the middle, where I have shown an interpolant, you are permitted to. You have to keep everything in the same row, but you can permute them in the row, but keep track of all the interchanges that you make in permuting them, and take the product of those plus and minus ones, and then do that in all possible ways. So actually, if there are repeated letters in your monomial, you can actually have numbers larger than plus or minus 1, larger or smaller than plus or minus 1. Then you do the same for the non-standards. You get two integer matrices, and you multiply this one by the inverse of this matrix, and you get you interpolate all the interpolation formulas. What I've shown you here is a slight adaptation of Rutherford's method, so that it works for uniform matrix. And that is as far. My purpose in this lecture was to show you the new stuff about that, but then about 3 weeks ago I found a counterexample. so I'm still at the level of knowing only uniform matrix, how it works. So now it's up to you to handle the ball. Shall I erase, or you do what you like? Thanks, Frank.
Well.
Well, the red one is a little. The red one didn't seem to work on me. But didn't do red one off.
Oh, I didn't.
Charles, did you bring the thermos of coffee in from the boot?
Covering the what?
The thermos of coffee that Didier